Problem 14 is another product mix problem. This time we're making a decision which of 8 different projects to fund or to undertake. We have 40 management scientists available and $300,000. And if we take a look at the information that we're given, we have an estimate of how many management scientists each project will take and what the expenses will be. We also have expected profit for each of the projects. So our decision variables will be the decision to take on project I, except I from 1 to 8. And our objective function will be to maximize profit. 360x1 plus 820x2 plus 290x3 and so forth, running right down our profits. Our two resource constraints: management scientist, 7x1 plus 9x2 plus 8x3, and so forth. And that total has to be less than or equal to 40 management scientists. For our budget, 60x1 plus 110x2 plus 53x3, and so forth, has to be less than or equal to $300,000. Now, what makes this problem a little bit different is there is a logical requirement, a logical constraint. If project 2 is selected, project 5 must also be selected. And of course, if you haven't figured out by now, these decisions that we're making whether or not to undertake a project are binary constraints, or binary decision variables. And with the binary decision variables, we can construct logical constraints that will enforce things like, if project 2 is selected, project 5 must also be selected, but not vice versa. And that's an important distinction for this particular constraint. Now, we are looking at projects x2 and x5. And with binary decision variables, there are 4 combinations of decision variables that we can set up. Undertake neither project, only x5, only x2, or both x2 and x5. This constraint, once again, if we undertake project 2, we must undertake project 5, but not vice versa. So this first combination meets that criteria, not taking either project on, taking x5 only, or taking both projects, taking x1 and then x5. But this is the condition that we do not want. We don't want to take x2 without taking x5. We need to come up with a relationship between x2 and x5 that will pass 3 of the 4 possibilities but fail in this condition. So relationship between x2 and x5. Now there are 2 different things that we can do between these variables. We can add them or we can subtract them. 3 different relationships: a greater than equal to, less than equal to, or strict equality. For the right-hand side value, we've got 4 possibilities: 0, 1, -1, or 2. And if you think about these different combinations here, you'll see that we cannot come up with a -2 for a right-hand side value. So we have two possibilities: addition, subtracted, 3 relationships, 4 right-hand side values, and that gives us a total of 2 times 3 times 4, 24 different constraints that we could come up with. We're looking for the one constraint that does satisfy all of these. And we might start by adding x2 to x5 greater than 0. Does that work? No, it doesn't. What we finally come up with is, if we go through different combinations, x2 minus x5 has to be less than or equal to 0. That passes the first condition. 0 minus 0 is less than or equal to 0. 0 minus 1 is less than or equal to 0. it fails in the third. 1 minus 0 is greater than 0, it's 1. And 1 minus 1 is 0. So again, this is the constraint that we are looking for. When we go to the spreadsheet, we've got projects set up in row 1. We've got the decision to accept the project in row 2. We have the profit in thousands of dollars in row 3, expense in thousands of dollars in row 4. We've got the number of management scientists that we're using in row 5, and row 8. X2 has a coefficient of positive 1, X5 coefficient of negative 1, X2 minus X5 less than or equal to 0. Sum product of decision variables, absolute, and coefficients. Copy that and paste special formulas only. And we can bring up solver, reset all. Target cell. We'd like to maximize profit by changing cells. Subject to constraints. These are all less than equal to. So left-hand side less than or equal to the right-hand side. Decision variables must all be binary. Options. Because of that binary, I don't need to assume not negative. Binary by definition is not negative, but I do need to check linear model. And solver finds a solution. We take project 2, 5, and 6. And notice that because I selected project 2, I also got project 5.